Heinemann Higher, Chapter 9 on integration, mixed questions, exercise 9R at the end. Number 14, I have to state the rate of oxygen consumption, so I've got a differential equation. It's given by this formula, where T is the time in minutes, I presume, since the rate is in centimetres cubed per minute. What volume of oxygen is used during the first 5 minutes after exercise? Well, the first thing is this: if that's the rate of oxygen use, that means R is the rate of volume, is dV by dt. So it'd be better expressing that as dV by dt is 58, and while I'm at it, I'll put that back up to t to the negative a half. That's the differential equation to be solved. Sounds fancy, differential, it just means you've got a derivative. How do you get rid of that? Anti-differentiate it. In other words, integrate it. So V is just going to be the integral of 58t to the negative a half dt. It says during the first 5 minutes. Well, what does this look like actually if you're to do that? The formula for this rate of change, for dV by dt, the rate of change with time, is this, which is a reciprocal. It doesn't matter if it's a square root, it's still a reciprocal, and they all look more or less the same. It's going to look something like this. And what it's saying is, what's the total amount used in the first 5 minutes? So I'm looking for the area up to here. I'm looking for this part here. Now there is a wee nasty thing here about asymptotes, but this one does have a limit here. So it's just a case of evaluate it from 0 to 5. So that means it's the volume used will be the area under the curve, which is from 0 to 5 of 58t to the negative 1. I could take the 58 out. It makes little difference in this case because it's so trivial. So it's add 1 to the power, so it's up to half. Divide by half is the same as multiplying by 2.1. Work it out at 0, work it out at 5. So in this case I'm going to have, well, that's 116, unfortunately, root 5 minus 0. So that's my answer, 116 root 5 centimetres cubed per minute is the best answer because that is completely accurate. However, the units are wrong because it's a volume, so it should just be centimetres cubed. If you want to compare it to answer at the back of the book, you'll need to use your calculator. And there you get 259.3838 and so on, which is 259.4 centimetres cubed per minute. In for a penny, in for a pound. That's centimetres cubed again. But once again, that is the better answer unless it asks for a decimal. Right, that was question 14. Now, as an alternative to taking this and interpreting it like question 13 as area under a curve, you could consider this then, I'll put this back the way it should have been because it was a volume, dV by dt equals 58t to the negative a half, simply as a differential equation that needs rearranging back into the form of V equals, and then finding the constant using initial values. So I've got V equals, that'll have to be the integral of 58t to the negative a half dt, which then gives you the same as before, a half. Divide by a half, that's the same as multiply by 2, and 2 times that's 116, plus some unknown constant c. And at t equals 0, the amount of oxygen used was also 0, which then lets you say that that means that c must also be 0. So you've got the formula V equals 116 root t plus 0. Then if t equals 5, that means that V is going to be 116 root 5 centimetres cubed as before. Just treating it as a differential equation with initial values.